All right, so in this video, we're going to be looking at applying transformations to a function. So typically, transformations are applied to base graphs. So the simplest versions of the graphs that we have from our library of functions. So x squared, 1 over x cubed, square root of x, those kinds of basic functions. And we apply transformations to them, compression, stretching, reflecting, or shifting in order to adjust the graph to achieve other kinds of functions that have similar shapes, but are maybe situated in different ways or increase or decrease in slightly different ways. So we're going to look at all of the transformations that we can perform on a function and then put them all together. So there are 6 things that we can do to a graph. We can horizontally stretch or compress it. And whether we're stretching or compressing is going to be done by a multiplier. And the size of the multiplier is going to be the difference between whether we're stretching it or compressing it. So we treat them together. We have horizontal reflections, and then we also have horizontal shifts. And then we have the same combination of things that we can do in the vertical direction. We can apply vertical stretches or compressions. Again, these will be achieved by multiplying by something, and whether we multiply by a large number or a small number will depend on whether we're stretching or compressing. Vertical reflections, and then also vertical shifts. Now, typically, we would apply all the horizontal changes first, and then we would apply the vertical ones. And generally, we want to do them in the given order. So applying the multiplication steps first, such as the stretching or compressing or the reflecting first, and then applying the shifts last. But we're going to go through these one at a time rather than applying all of them simultaneously. So we're going to start with the shifts, even though they're technically the last thing that you should be applying. We're going to try to apply them one at a time. So we do not have to only apply these in function notation or to common functions. We can actually apply them to things like circles as well. Now, these are some examples of some of our basic graphs that we're going to be working from. We've got an x squared graph. We have the 1 over x graph. We have the square root graph, which will be really useful for showing reflections because it lacks any symmetry at all. We have the circle, and then this is a sine curve. Now, we're going to be de-emphasizing the sine curve because the trig functions, because typically we cover transformations in an algebra course before we've encountered any of the trig functions. But the trig functions are very interesting in terms of their transformations because they actually behave in terms of the vertical and horizontal compressions and stretching a little bit differently because they have so many zeros. You can actually distinguish one from the other in a way that is much more difficult to do than when you're working with traditional functions, where you can always move them from one side of the equation to the other. Now, we're going to start with an example of a circle. If you're starting with a circle centered at the origin, if I want to move the origin, the center of the circle off the origin and recenter it at 3, 0, I can apply a horizontal shift. So I have my starting circle and I want to move it over so that the center is here. Then what I do is I replace my x in my equation with x minus 3. And so that is what's going to shift the circle over. Essentially, the value 3 is now going to behave like 0 did before. Because if I put 3 into my equation, then 3 minus 3 is 0. So that's going to be acting like the position 0 did in the original circle equation. So similarly, if I want to move my center over down, for instance, down from the origin to 0, negative 4, that's a vertical shift. And so what I'm going to do is I'm going to replace the y in my equation with y minus the shift that I want to make. So y minus a negative 4 becomes y plus 4. And so if I replace my y in the equation with y plus 4, that's going to have the effect of shifting the equation downward. by 4. So again, essentially what we're doing is we're saying, well, I want -4 to behave like my 0 did before. And so now if I instead of putting 0 into my equation and getting 0 out of this term, now I'll put -4 into the equation and I'll get 0 out of this term. And then I can apply both shifts simultaneously. If I want to move the center to 3, -4, I would shift the x coordinate by subtracting 3, and I would shift the y coordinate by subtracting -4. And then that's going to get me that horizontal and vertical shift at the same time. Now, we could also do this, of course, for traditional functions, but in the function notation, the y is on one side of the equation, and typically we end up applying our transformations on the other side of the equation. And so there's going to be a shift in sign. If you're applying them all on the side of the equation where the variable is sitting, there is a certain consistency in that the shift is always going to subtract from the side where from the variable it's being shifted. But when we work with function notation, we're actually going to shift it on one side of the equation and then move the constant over to the other side of the equation so that the function notation is by itself again. So you'll see this change in sign behavior going on. And there's going to be similarities for stretching and compressing, where there's going to be a flip in orientation of some sort, but that's because we're moving it from one side of the equation to the other. So let's consider our basic x squared function. Our parabola starts out looking like this, and the equation is f of x is x squared. Now, if I want to shift the graph horizontally 2 units to the left, in other words, so that the base of the graph is at -2 instead of at 0, then I replace my x with x minus -2, which is x plus 2. And then I stick that inside my function. So where the x was, instead of it's x squared, it's now x plus 2 squared. And so that is going to get me this graph down here, where I've shifted my parabola over. It has all the same shape as everything had before, but now the 0, the intercept where it's bouncing off the axis, is going to happen at -2 and not at 0. So again, we're treating the sign is the opposite because we're treating -2 like 0 was being treated before. So we compensate for it by adding 2. Now, if I want to shift my y function, and I want to actually shift that, if I want to shift it up by 1, to be similar to what we were doing with the circle, I would do the opposite on the side with the y equation. So y minus 1. But then what I'm doing is I'm actually moving it over to the other side of the equation, and it's turning into a +1 on the other side of the equation. So I can think of this either as always do the opposite on the side with a variable, or I can just say, okay, well, if I want to shift something in function notation, I subtract when it's x and I add when it's y. But I'm adding on the opposite side of the equation. So I'm taking my function and I'm increasing the value by 1 in order to shift it up by 1. But on this side of the equation, I'm treating -1. I'm treating 1 as 0 was, so I'm subtracting 1. Now, so like I said, this can be a little bit confusing. So the idea that I want to suggest here is choose a method to remember this that is useful for you. I found thinking of it always as keeping the signs the same, transforming it on the side of the variable always to be the same, always subtracting or remembering it as flipping the sign. Think about it in terms of one way that helps you remember it. And what helps me remember it and what helps you remember it is not necessarily the same thing. But you can think of it in terms of always flipping. So always subtracting if you're on the side of the variable, or that x and y do opposite things. Again, because we're going to apply them on different sides of the equation. In function notation, if we apply transformations on the side of the x, we're going to do the opposite thing that we would do on the side of the y. And either way, especially when you're getting used to this, you always want to confirm, if you have a calculator, confirm the result by graphing if possible. You want to be able to do this without having to rely on the calculator, but the calculator can be really helpful in terms of making those transformations sort of more intuitive, because you can think about, okay, so I'm going to do this, and then let's make sure that that's in fact, my intuition is telling me to do the right thing. Now, in function notation, everything that applies horizontally is done inside the function notation, whereas things that apply vertically are done outside the function notation. So if I'm doing, if I want to transform a function by shifting it to the right, I would express my function notation as h of x minus 5. So if my h function is originally 1 over x, then this is telling me I'm going to replace x in my equation with x minus 5. And so 1 over x becomes 1 over x minus 5. And so it takes this 1 over x graph and shifts that vertical asymptote to now occur at 5 instead of at 0. If I wanted to do a vertical shift, then I would write h of x plus 3. So that transformation is happening outside of the original function notation. And so that's telling me that I'm going to take my original 1 over x function and I'm going to add 3 to it. And remember, if I had been doing this by replacing y with something to do this shift, it would have started out as y minus 3, and then I add the 3 to the other side of the equation, and that gets me that upward shift. So again, the graph is going to look exactly the same as the 1 over x, but now instead of having a horizontal asymptote at 0, the horizontal asymptote is now up here at 3. Now, for reflections, for those to work really well, we're going to have to look at a function like the square root of x that doesn't have any symmetry. Because for some of our functions, like 1 over x has odd symmetry. And so certain kinds of transformations are just not going to show up. Or they're going to show up the same when you do vertical reflections and horizontal reflections. Same thing for like even functions. Some of them will show up and some of them won't show up at all. So the nice thing about the 1 over x, the square root of x function, is that it has no symmetry at all. It's not even, it's not odd. And so it's going to show all of the reflections to be a unique version of the graph. So we're going to start with horizontal reflections. And the idea behind horizontal reflections is we're going to take our x and we're going to replace it with minus x. So it's the same test that we do to test for symmetry, but now we're just actually permanently putting it into the function. Now, if I take my square root of x graph, it looks like this over here. And when I apply the horizontal reflection, I replace x with minus x, the graph flips over to the other side and is now pointing from 0 and then through the negative values, because the negative will make other negative values into a positive, and then you can apply the square root. Whereas if you put a positive number into this reflected graph, you're going to get a negative number, and that's going to give you a complex imaginary number as the result of the radical, and that you can't graph that. So it's going to take this graph on the positive side, and putting a negative in front of the x is going to flip it over to the other side of the graph. Now, if we start with a 1 over x graph like this, and I replace x with minus x, I'm thinking of this as a horizontal transformation. It's going to flip this first quadrant over into the second quadrant, and the third quadrant over into the fourth quadrant. And so it's going to flip it horizontally. But this is exactly the same graph that I would get if I did a vertical reflection. And so that's why the 1 over x graph is not as reliable in terms of being able to tell what the result of the reflection is doing, and the square root graph does a little better. because in the 1 over x graph, horizontal and vertical reflections look the same. Now, if we go over to vertical reflections, then these are going to show up best with even functions, but they will show up identical with odd functions. And then the square root of x graph is going to be distinct in both cases. So this is our original square root graph, and what we actually are doing is we're applying a negative to the y function, and then we're moving it over to the other side of the equation. So we're applying it to the outside of the function. So if I apply a negative to the outside of the function, I take my square root of x and I flip it over the x-axis. That's a vertical reflection. And it's now, instead of in the first quadrant, it's now in the fourth quadrant. Same thing for my x squared graph. If I have my original x squared graph and I put a negative sign in front of it, it flips it over the x-axis. That's my vertical reflection. And I end up with this upside down parabola. But as we saw with the 1 over x graph, if you apply a negative to the denominator or you apply it out in front, you end up with the same graph. So a horizontal and vertical reflection are the same. So you can think of this as the original function, and I can think of it flipping horizontally, or I can think of it flipping vertically, and I'm going to get the same result either way. Now, because the square root function doesn't have any symmetry at all, I can actually apply both horizontal and vertical reflections and get a distinct graph because I can't distribute these x's through the square root. So if I apply a horizontal reflection under the radical, I move it from the first quadrant to the second quadrant. And then if I apply the negative on the outside, then I move that from the second quadrant to the third quadrant across the x-axis. And so negative, the square root of negative x, is now in the third quadrant. So I can actually move my square root into any of the 4 quadrants that I want. Now, to describe these transformations in function notation, the horizontal reflection, again, anything horizontal is inside the function notation. So this is f of negative x. So that tells me replace x with negative x. And the vertical reflection is negative f of x. So apply the negative to the whole function. Now, when we do stretching or compressing, this is also achieved by multiplying by something. And so technically the reflections and the stretching and compressing can be done together because they're both achieved by multiplication. So one thing to kind of keep in mind, though, is that when you stretch or compress or reflect a function that already has a horizontal shift on it or a vertical shift on it, when you apply like a negative to the entire function, you're actually changing the value of those shifts. And so this is generally why we want to do the multiplication steps first, and then when we're applying multiple transformations, and then do the shift last. Because that's going to we're going to apply the shifts last, and so that will make sure that we preserve the value of those shifts. Now, generally, reflections are achieved, as we said, by multiplying by a -1. But if I multiply by a small value or a large value, I'm going to get either stretching or compressing, again, depending on which side of the equation I end up multiplying on, whether I'm multiplying just the x, whether I'm multiplying by the entire function. And so we're going to see some examples. And again, we're going to see when we're not dealing with just changing negative signs, we're actually going to see that there's another like opposite effect going on. So if I'm multiplying in y versus multiplying by x, that the effect is going to be the reverse. So similar to the shifting, if we do it on one side of the equation versus the other side of the equation, there will be a change in the behavior. All right, so horizontal stretching and compressing. So this is done by multiplying inside the function. So I'm going to multiply x by a constant. If I want to compress the graph in the horizontal direction, so that means I can essentially make it skinnier, then a should be a number on the interval 1 to infinity, so a number bigger than 1. If I want to stretch the graph horizontally, then my multiplier needs to be a number between 0 and 1. So again, here is my basic function, 1 over x squared, y is x squared. And if I replace, if I use a multiplier of 1/2, I'm actually going to get this graph right here. So again, we want to think about this. Why is this working this way? Essentially, on this original graph, if I put 1 in for x, then my y value on the graph will be 1. But when I multiply by 1/2, I'm saying, no, I don't want to get 1 until I get to 2, because 1/2 times 2 is now 1. And so that's going to make the value of 1 further away from the origin. And so that's going to stretch out the graph horizontally. If I want to get to that 1 value, for example, faster, so I want to get, for example, if I multiply by 3, I will get to that overall value of y equals 1 by the time I get to a third and not 1. So it's going to go up, it's going to vertically increase more quickly. And so it's going to get large faster. And so it's going to look like it's compressed horizontally. So if you multiply by x by a small number, stretch it out. If you multiply x by a large number, then you are squeezing it in that in the opposite direction. You're compressing it by that factor. Now, if you do vertical stretching and compressing, we do these things outside the function. So what we're going to do is essentially stretching and compressing in traditional algebraic functions, not trig functions, but in traditional algebraic functions, vertical stretching and compressing are actually related to each other because you can always pull the constant out. So if I take my 1/2 x quantity squared and I actually do that math, I end up with 1/4 x squared. So even though I was originally trying to stretch horizontally by a factor of 1/2, I'm actually stretching the graph vertically as well. So because I can always move this 4 over to the other side of the equation, and again, I'm taking my original x squared function and I'm making it shorter in this case. And so I can think of this as compressing the y value or stretching the x value, because one does the opposite. Same thing for my 3x quantity squared. If I distribute my square and I apply that, I get 9x squared. So again, this is essentially stretching vertically by a factor of 9. I'm getting, not when x is 1, I'm not getting to 1, I'm getting to 9. So I'm stretching that y value. And again, that's a vertical stretch is essentially equivalent to a horizontal compression. Again, for most of these standard functions, you can always pull those constants out and then they become versions of the other kind of stretch or compression. So there's a change. Horizontal compression, vertical stretch. Vertical compression, horizontal stretch. Now that won't be the same with the trig functions, because these 2's, for instance, if I have sine x versus sine 2x, I can't actually pull the 2 out. So the sine 2x is actually changing the locations of my zeros. So this would be a traditional sine graph. Sine 2x is going to say, oh, I'm going to go through my zeros faster. So that is still doing a horizontal compression using that multiplier bigger than 2. It's going through those zeros more quickly. But if I apply the multiplier on the outside, that's not actually changing the locations of the zeros, it's just changing the value of the y's. And the maximum value on the traditional sine graph is 1. And so now multiplying on the outside by something is going to make that y value larger. So because I can't pull my coefficients out with those trig functions, I can actually see the results of the horizontal stretch and compression applying differently. So I can do both of them at the same time and get very distinct results. So I can keep my zeros in the same place and make the graph taller, or I can keep my zeros and change the location of the zeros, or even how many of them there are in a given region without changing the height of the function. Whereas, again, with traditional functions, x squared, 1 over x, things like that, there's always a way to think of it as pulling out those coefficients and transforming compressions into stretches in the other direction. But you can't do that with trig functions. And so you do get to see the distinct behavior of the different kinds of stretches and compressions. That's why they're separate things, because even though they're related to each other in some functions, they are completely independent of each other in other kinds of functions. So we're going to walk through some examples of actually putting all of this together. So we're going to apply transformations of the graph to 1 over x. So we want to shift left by 1, reflect vertically, and then shift up by 6. So, and then sketch the graph. Now, in function notation, we would write this as f of x plus 1 with a negative sign out front because that's the reflection. That's a vertical reflection. And then shift up by 6, so that's the plus 6 on the end. So if I take my 1 over x, I'm going to have the negative out front. My x plus 1 will replace my old x, and then the plus 6 on the outside, and I get this graph. If I want to apply the following transformations to the graph of sine x, so I want to horizontally stretch by 2, I want to horizontally shift to the right by 1, I want a vertical reflection, and I want a vertical shift by 3. So what's happening here? So I'm going to start with sine x. I want to do a horizontal stretch by 2. So a horizontal stretch, I multiply by 1/2 because it's a factor of 2, but to do a stretch in the horizontal direction, I have to use a fraction. So it's 1 over 2. So that's my 1/2. I want to horizontally shift right by 1. So that's our x minus 1. So notice I basically started with my 1/2 x, and then I replaced my x with x minus 1 inside my multiplier. So that's the horizontal stuff. Then to get a vertical reflection, I put the minus sign on the outside, and then the vertical shift by 3, assuming it's positive, I would add 3 outside. And so my sine x graph is going to look like this. Essentially, again, I just take my function notation and I stick my sign in place of that. So it's minus sine of 1/2 x minus 1 plus 3. Now I could distribute this 1/2, of course, and it will look slightly different, but it's fine to leave it just like this because it's very easy to see what transformations were applied. Now, if I want to list the transformations that were applied to a function, again, I'm going to have to modify some of the notation a little bit so that I can tease out what the particular transformations are. So I'm going to have to factor out this negative sign so that I can see the direction of the vertical shift here. So this is going to have a vertical shift of 1. So if we work backwards, a vertical shift of 1, that's outside the root, so that's why it's vertical. There's a vertical stretch of 2, again, that's outside the root. There's a vertical reflection, because again, that's outside the root. Then there is a horizontal reflection, that's this negative inside the root. And there's a horizontal shift of 4 to the right under the root. Now, if you go ahead and you graph this, you'll actually see that what used to be the 0, where the square root graph ends, is actually now happening at 4 and not at -4. So this +4 might lead you to think, oh, it's x plus 4, therefore the shift is in the negative direction. But no, it's actually in the positive direction because we have to factor out that negative sign because the negative has to be applied before the horizontal transformation can be applied. Now, we can also apply transformations to a set of points. So we're going to consider the points 3, 2, 1, 1, and -1, 4. So you can imagine, for instance, a graph that has these as endpoints, and maybe we have lines connecting the dots or something. So when you're applying transformations to a piecewise graph or on a curve, it's drawn on a graph and you don't have the actual equations, then you want to apply these transformations to the points, and then you would connect the dots in similar ways to what was drawn on the original graph. So here we're going to apply the following transformations to these points: a horizontal reflection, a horizontal shift left by 2, a vertical stretch by 4, and a vertical shift down by 3. So we have 4 total transformations. So under the horizontal reflection, we're going to apply that reflection to the x points only because horizontal affects the x coordinate. So horizontally reflected from positive to negative and negative to positive, our 3 will become a -3, our 1 will become a -1, and our -1 here will become a +1. Then we apply the horizontal shift left by 2, and so these points that we've already transformed, we're going to subtract 2 from all of those. Now, again, when you're dealing with points, you apply these transformations slightly differently than when you apply them into the function. So it's not +2 in order to get the leftward shift. We're literally just going to shift them left by 2. So we're going to subtract 2 from those values. So -3 minus 2 is -5, -1 minus 2 is -3, and then 1 minus 2, we're back to -1 again. Again, these are horizontal transformations. They're only affecting the x coordinate. But now our vertical transformations are only going to tackle the y coordinate. So if we want to do a vertical stretch by 4, that means we're going to multiply the y coordinate by 4. So our previous value was 2, we multiply by 4, we get 8. Here our previous value was 1, and we multiply by 4, and we get 4. And here our previous value was 4, and we multiply by 4, and we get 16. And then finally, we apply the vertical shift down by 3, and that finally gives us 8 minus 3 is 5, 4 minus 3 is 1, 16 minus 3 is 13. And so then to apply all of our transformations, we would then plot these points, and then we would connect the dots in the same order that we connected them in on the original graph, if indeed it was a graph. Because again, you can apply these to individual points, or you can apply these to whole graphed functions by just applying them to basically the change points, the end points of the picture.